Good afternoon, good evening, and good morning. Greetings from Stanford University, and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber event. My name is Renate Fruchter, founding director of the PBL Lab, and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. For this purpose, each global student project team prepared a video story of their project evolution. These stories are reviewed and assessed by about 30 industry mentors prior to the May 8th cyber event. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class.
So we are Team River, and we consist of me as architect, Jenny and Niklas as structural engineers, Karen as MEP, Kosuke and Mina as construction managers, and Julius as lifecycle finance manager. And we are in Weimar in Germany, and we are in a UNESCO World Heritage Zone, so we have to be careful around the beautiful nature and the surrounding buildings. We are placed in the middle of the Ilm Park, and to the east do we have the Ilm River, and to the west do we have the amazing historical city. In the middle here do you see the construction site, and to the left do you see the castle, and to the right do you see the horse house. We investigated the context to get inspiration to our building. We want to relate ourselves to the castle, which is a stone building with wooden shutters, and we want to relate to the existing Weimar University building, and we want to get inspiration from the landmarks, the tower and the bridge, which is in the river, and it's made of copper and cobblestones, and in general we learned that the city is really geometric in the topology, which is also what we want to achieve in a modern way.
The weather in Weimar is seasonal, which creates the need for extra ventilation during summer and heating during winter. A strong wind is coming from southwest, which gives the opportunity for natural ventilation. The outdoor comfort is good between April and October.
So at this point, do we already have a lot of constraints that we can turn into design criteria and challenges? We have flooding from the river that we want to sustain ourselves from. We have a slope at our side. We are in the UNESCO World Heritage Zone. Our owner have a wish to preserve trees. We have a narrow construction site, and we have to relocate an existing pathway to make space for the building. And our goal is to achieve all three types of sustainability, and we want to do that by focusing on the user, being energy efficient, and implement flexibility. And more than our team goals, have you been given 3 challenges about resilience, where we want to sustain the future, DPR, where we have to value if we want to industrialize or not, and IT, that is about how we create data between disciplines.
BGNB is the German equivalent to the International Building Certifications BREEAM and LEED, and is the prime standard in Central Europe. The sustainability criteria, as you can see here, are based on the United Nations Sustainable Development Goals. During the design process of Buttercup, we especially focus on these 6 values to score best with the very strict German Sustainable Building Council.
So what are we actually designing for? We're designing for the users to create a student environment. We're designing to giving something back to the context, and we're designing to the future to sustain any changes according to climate change and according to use of the building. And for the whole group, really to understand our users, we did create 2 personas, because this is our 2 main users of the building. We have Tim Fischer, who is a research student in our building, and Martin Becker, who is a professor in the building.
Our 2 concepts from the winter presentation were the Buttercup and the linkage. There was high competition between the 2 Buttercup alternatives, natural, which was purely wood, and hybrid, which was a mix between steel and concrete. Natural achieves high scores in design aspect. It has less construction issues and has higher environmental performance. Actually, it comes second after hybrid in functionality, sustainability, and economical aspects. The graph shows the final scores across the different metrics, so we decided to go with the Buttercup Natural to be further developed in the spring quarter.
From before the winter presentation, the design evolved from the concept Buttercup, and you here see our Buttercup building. The buttercup is this flower that constantly relates to the sun and shapes its petals so a warm and pleasant spot is created in the center. This is the reason why the buttercup is super attractive to the insect, as our building should be for the occupants.
So first of all, did we extrude the building footprint to make more space for the insects. Then we wanted to make sure that the connection between the park and the water was kept. The cantilevers, they were adjusted between structure and architect. And the atrium was created to having daylight and a warm spot for our insects. And then the facade design, it was adjusted between the architectural impression, prefabrication, daylight, and heat gains. And at the first floor, we did locate the more public rooms, so you're able to socialize more. We have classrooms, auditorium, and a cafe. On the second floor, we have workshop areas and some group offices. So this is mainly the floor for the students. On the 1.5 floor, we have a big collaboration and flexible area and 2 big classrooms. This place is ideal for student presentation or creative work where clear space is needed because there are no columns in this large lounge area due to post-tension structure. On the 3rd and last floor, we mainly have space for employees. We made private offices a little bit smaller than the brief suggested to make extra space for socialization, because socialization is really the key to achieve creative, innovative, and collaborative work environment. We created a nice break room with space for all the employees and flexible space to work or have a less formal meeting. And here do you see how we utilize the different functions on the different floors. So the large classrooms is on top of the auditorium, where the bigger architectural height it's needed there, and the rest of the building to have 3 stories. And now I would like to go through our building as how a typical day will be for either Tim or Martin or 2 personas. And both of them, they arrived to the university a bit before 8 in the morning. And Tim, he parked his car at the bike path, and Martin, he arrives by car, so he walks directly to the main entrance. The first lecture, it's in the auditorium, where Martin, he's the teacher, and Tim, he's together with the other students. And this is how the auditorium looks. And the structure and MEP system is completely symmetrical to keep it as simple and as beautiful as possible, and it's not necessary to have an additional ceiling to make this space nice looking. And in the auditorium, that we really focus on the future of teaching. We think the future of teaching is more integrated between students and professors. Therefore, we shape the building as a U to make sure that people can see each other. The students have access to an app on the device so they can control one of the small smart boards. They can also ask questions to the students in one of the other small whiteboards. And a presentation can be ongoing on the big whiteboard. We have implemented tinted windows so you're able to control the daylight in the room. And it's actually not necessary to have daylight in the room, but in case of a renovation later, it will be really good that you don't have to penetrate the envelope to create a window for daylight. We have sound sensors so the teachers will be aware if he or she is speaking too low. And to optimize the room for speaking, we did investigate which type of reflection, absorption, and seating will affect our acoustics. We found out that the best solution is a straight auditorium that completely absorbs the sound on the walls to prevent any echoes, and therefore it should reflect the sound on the ceiling to make sure that people in the back of the room can hear the same amount as people in the front, but seating doesn't have an effect on this. We investigated the site in the room and from different perspectives, and you see the worst view here. And even though it's the worst view, you can see the whole stage area, but by turning your head less than 45 degrees. And also, as mentioned, we are having this app for the users, so they can use this to track their schedule, access the auditorium screens, but also to access stores inside the building and access the elevator, so you don't have to touch any buttons or do anything that can give you germs on your hands. So after the lecture, both Tim and Martin have to research. And Tim, he goes to the student office to research, and Martin goes to one of the faculty offices. But actually, the offices are the exact same size, so therefore it's possible in the future to rearrange any of the furnitures to transact a student office to a faculty office or the other way around. And at noon, it's lunchtime. So today goes Tim to the cafe and orders some food, and Martin goes to the break room with his own lunchbox. After lunch, did Martin arrange a workshop in the labs for the students. And we designed the lab as one big workshop room with dividing walls, the room dividers, the chairs, the tables, they are on wheels, and they can therefore be moved into any position. That means the space is optimal for a lot of different use. The furniture can also be moved out of the room and into the big storage room we are having, so you can completely transform the space. Our former space is former server room space, it's turned into a storage room because we're having cloud service instead.
Martin and Tim appreciate their university's modern state-of-the-art data setup that allows them to access their research data from everywhere, inside and outside the building. The cloud computing, shown as the bright slope, is more cost-efficient over time compared to the server room, indicated by the dark slope. The server room requires general overhaul after 10 years due to outdated technology and is to be replaced after 20 years. With cloud computing becoming more and more established, user fees will reduce. The cloud service offers flexibility that can be adapted to changing demands anytime.
So at the end of the day, Tim have some group work and Martin, he have a meeting, and these are being held in the collaboration spaces in the lounges. And to be able to design for innovative students, it's really important that we have different places in the building where we encourage this teamwork. So here do you see some different workstations on each floor. They do all have these flexible furniture in the room, so they can be transformed easily. The floor is made of end-grained wood, so it does sustain the movement of the furniture during the lifespan of the building. Actually, also the yellow fabric you see is working as acoustic elements too.
On our way to decide the floor material, we were looking for something durable, easy to maintain, and a regional product to reduce our carbon footprint. The end-grain parquet appears to be the product of choice. The alternative would be an OA floor that was not ideal because it requires frequent replacement. Furthermore, it has very bad water resistance properties. Tiles are slippery during winter and expensive to replace, as our owners claimed. The end-grain parquet is the hardest wooden floor with excellent durability, and it can be grinded whenever it is worn off. Grinding the surface is very sustainable and cheaper than replacement. In addition, this is a German product that couldn't be more sustainable due to the embodied carbon of the wood and its regional heritage.
So in the middle of the building, we have this really flexible auditorium for the insects. During a regular day, it's used as a lounge area. And due to high heat gains in the summer, we did implement these tinted glass here too. This can also be utilized for presentation mode, and it's also ideal for both daily use and also for rental hours. In the summer month, this atrium can be opened to utilize the space as a stage area during rental hours, so they can be held a concert for the public using the outdoor plaza.
As part of the PPP, we commit towards our owners to offer them the best possible rent. In doing so, we are in a constant trade-off with the value for money we can offer. However, through the yet introduced ideas, we are able to deduct the annual rent tremendously. The greatest impact have the externally led cafe and the auditorium/stage area.
And now we will introduce the MEP concept and the design building system. The primary systems in the building is a heat pump connected to solar panels on the roof. The building is mechanically ventilated through air handling units, and a water loop is created with water collection on the roof. The larger volume rooms have displacement ventilation and are naturally ventilated through night during spring and summer. All the rooms has VAV controlled ventilation. Our goal is to be energy efficient, and that is why we implemented a heat pump running on solar energy. The heat pump system is claimed to be 5 to 8 times more efficient than other heat pump systems. The heat pump distributes pleasant warmth to all the rooms, ensuring the insects in the building to keep up. Other than that, we are using a rotary heat exchanger that makes the ventilation system more efficient. The reason why we chose to run on electricity from the sun is that the owners in the future has the opportunity to couple up on the district energy supply when suppliers in the area can provide 100% renewable energy. In this way, they can be more coherent with the community. Then they can get energy from the community when the solar cells are not producing enough energy, and give when they produce more than needed. As you see here, we produce more energy than we use. Since the aim is to be a zero energy building, this is a guarantee that the goal is realistic, since the production of energy as well as the use easily can vary with 40%.
The PV panels contribute significantly to the rent reduction, since we produce our own energy on site and do not rely on increasing energy prices. Without offering additional value for money to our university owners, we could reach an annual rent that is as low as €800,000.
To create optimal thermal comfort in the building together with a low energy use, different implementations were made. The shading and change of cooling set points were needed to create better thermal comfort, even though it was not helping the energy consumption. Improving the building, even though having less infiltration, especially made an impact on the energy performance. To create better user comfort, we have chosen an acoustic diffuse ceiling in all smaller rooms, which minimize the noise and risk of draft. The air is nicely distributed in the room to evenly distribute with evenly distributed heat panels. The air will stay clean due to HEPA filters. On the first floor, you see the MEP room and how all the rooms are installed with heat panels and electrical power plugs along the exterior walls. Larger volume rooms one wing of the building is provided with displacement ventilation from one air handling unit, and smaller rooms is provided with diffuse ventilation from another air handling unit. And here you get an overview of the whole building with the MEP equipment on the first floor and on the roof.
Okay, now we'll present you a selected structural system and evaluation of our floor sandwich height through a collaboration of structure and MEP. As you can see, our structure is designed mostly in timber. We have concrete floor for balancing groundwater pressures, and to increase lateral stiffness of the building, we have two remote CLT cores. We have glue-lamp beams and columns for gravity system, except for the places where we have high density of MEP. Instead of diagonal braces, we have regular CLT walls to increase the stiffness of the cantilever through shear force. First and a half floor and second floor framing are combined with two different systems. In places where we have more MEP, that's on the north, we are using more steel and timber trusses. On the south, where we have higher floor sandwich and larger spans, we use post-tangent glue-lamp beams. Third floor framing is highly similar to second floor. Instead of glue-lamp beams on north cantilever, we are using trusses to allow flexible design of MEP. And on cantilever on the east, we have continuous glue-lamp beams to provide sufficient backspan. Roof framing is significantly different than other floors. We are having reduction of the columns in southern part of the building, so we are having higher post-tension beams there. We're also shifting bounding box of the framing towards inside to reduce because of the sloped column on the top floor. Here we will explain how we get to the selection of steel and timber truss. We consider different timber solutions in our design process to provide sufficient clear floor height without excavating more than necessary. Because penetrating glue-lamp beams would mean enormous increase in beam height and decrease of flexibility in our design, we consider different alternatives. We started design with topological optimization of the beams to determine the reduction of the section. At the end, steel and timber trusses were best design option for our walls. Then our MEP searched different shapes and sizes of ducts to find largest area of the duct to provide sufficient amount of supply and return air for each room.
An excavation and the integration between the structural system and the MEP system led to an architectural height of 2.8 meters in smaller classrooms and offices, and an architectural height of 4.2 meters in larger rooms and the auditorium. Integrating the structural system and the MEP ducts took progress when we utilized BIM integration software and also the cut opening tool. This way is an easy way to see the clashes, which ended up with being zero.
Because some trusses are exposed, our challenge was to ensure fire protection. Without any additional protection, we achieved our building to be resistant to 30 minutes of fire exposure. With coating bottom coat of the truss and increase of the section, we can exceed fire rating for 60 minutes. To protect steel web, we choose authentic stainless steel to limit the drop of material properties and achieve sufficient fire resistance.
We'd like to introduce some of our connections. We designed them for quick assembly and inconspicuousness. Some of them are hidden to protect them for fire, among others. Starting at the bottom, the columns are connected to the floor by this simple footing. They are not designed to take any moment. The CLT walls will be connected at the edges with the system to the concrete slab. When trusses join up, they will have this hanger to help transfer the loads between the joints. Beam-to-beam connections will be concealed as shown, and for the slanted parts of the columns, we went with finger jointing. The mid-piece was here necessary because the pressure under an angle parallel to the crane leads to a high reduction of the resistance. In the auditorium and above, we implemented post-tensioning to get this clear span of 14 meters without having very big beams or high deflections. The tendons are polygonal and will go through the columns and be anchored. In the field, you can see one redirection point. Talking to the CMs of our team made us aware of the limit of transportation and weight for the preferred cranes. Therefore, we had to divide the beam into parts. They are 12 and 5 meter long, including the cantilever. The rigid connections for the beams will be realized with steel plates around. To the load path. All gravity loads will be transferred by the roof slab and beams to columns and led downwards. At the location of the cantilever, shear walls gets activated. Lateral loads due to wind go through the floors and beams into the core walls, which carry the loads down to the foundation. Speaking of foundation, in general, we have strip foundation under the surrounding concrete walls and core walls. On a few spots, also single foundation. The piles came into consideration because the bearing soil is on around 1.5 meter depth under the first floor level at the right part of the building. Then the overturning moment of the large cantilever creates a tension force, which dead load cannot compensate. Additionally, uplift by water in a flood can be a problem. The micropiles we took work with the friction to the soil and will take all these loads. So we analyzed the deflections for the serviceability limit state. This is the displacement in vertical direction. Red is the largest. The building is not shown deformed here because it would be too messy. We get highest deflections on the left side where we have the auditorium and above the large classrooms with a lounge area in front. That is also the area where we put post-tensioning. This shows the deflection of the large cantilever. Another picture because we applied another load state. Through the stiff walls, we have the highest deflections located in the middle of the first field and at the end, since the floor is cantilevered in two directions there. The final deflections, as well as on the previous slide, include the creep deflections. The lateral deflections gets maximum in right direction at the large cantilever, since it is the farthest from the lateral system. As you can see in the graph besides, we stay in the limit for horizontal displacement in each story. Vibration analysis also belong to comfort. We need to ensure that floors will not bend too much or you bounce by walking. We grabbed here an example of a typical floor system we have in our building. For the calculation, the trusses were transformed into full beams with the same moment of inertia, in this case 200 by 460 millimeters. The system we have is quite stiff, so in the end all evidence is proved. The CLT floor itself fulfills the criteria when the span is smaller than 3.2 meters for this certain height. With our skeleton construction of wood, it is easily possible to rearrange walls. On this slide, you see permanent walls in yellow. They actually cannot be removed. The orange walls instead can be disassembled or moved and therewith create new space for future use.
For the flexible wall between small room and lecture rooms are planned as pre-finished assembly walls. About 35% of the interior walls are prefab and assembled on site. Although the price of products is higher, the cost of transportation, installation, and future renovation costs can be significantly reduced. The heating and electrical system are installed for other walls accordingly for easy relocation. The flexibility of the plan increases the long-term operation and resilience of the building.
Yes. As we experience right now, and as it has occurred in centuries, extreme situations can suddenly strike without any prediction. That can be due to pandemics or climate changes. That is why we felt the necessity to embrace the new ways of thinking in terms of being reactive and predictive to the future when we were designing our building. In our design, we aim to make it as flexible as possible to easily respond to the changes that will affect a whole population now and in the future. Our Buttercup building should be a place for recovering and well-being of affected insects. We will now explain how. Large building as university has the possibility to create space for beds and shelter in these situations. Here you see how fast the need can escalate. To avoid overloading the hospital, we here show how people in need should arrive to the hospital, to the university, where they get a test. If they have mild symptoms, they will be taken care of at the university or sent home after assessment. In our Buttercup building, they can have their time in insulation with care and rest, and either be sent home or to the hospital if their statement gets worse or better.
We have to make sure that we are separating the patients between stage 1, testing, stage 2, care under supervision, and stage 3, sick in isolation or step-up care. So our test area is in the auditorium where there is access from outside. We will have the cafe that will be utilized as a kitchen, and the patient ward will have 10 square meters for each person, and it will be located on the first and the second floor. So as further you go up, as more isolation rooms do we have. On the 1.5 floor that's utilized for staff due to that hospital beds cannot move into this spot, only wheelchairs. On the top floor is the most sick people, and we're also having showers on each floor.
An MEP system with flexible docks would make it easier to design the needed ventilation for the situation. The VAV makes it possible to design a negative air change rate, which is ideal under these circumstances. A HEPA filter will ensure a clean and healthy air, and all surface materials is chosen to be easy cleanable.
We are a public-private partnership. In our case, we construct the university building and operate it in exchange for an annual compensation. But are we also a hospital? During the pandemic, the building cannot be used at its original purpose. Since we want to contribute to the public well-being, we can utilize our vacant building. There are plural benefits. First, we can serve a good cause in supplying the additionally required space for hospital beds. Second, we can cover the cost for the building that are created either way with the little additional rent for the hospital. We aim to only charge as little as possible from our hospital tenant.
We also calculated the number of days it would take for an emergency transition to the hospital. Since there's no need to change the room layout, most of the work will be MEP works, but since the electricity, air conditioning, and internet facilities are already designed to work at the time of construction, the work can be minimized and completed within 2 weeks.
We will now lead you through 4 stages of our design response system for reducing flooding risk, to show you how we tackled our goals for designing sufficient and redundant response system that benefits also social and environmental sustainability. One of our challenges in our design phase was also flooding. To assess our flood vulnerability, we checked future and past prediction. As already shown, our building is affected with 200-year flood, and because of the excavation, we are increasing risk of flooding our building. Here we are showing you future predictions of climate change. We expect small change of flooding frequency already in near future, and in distant future, we expect increase of flash flood risk.
Before analyzing flood protection, we require accurate topography data. Our site is narrow and slope, however, unfortunately, the public data from Google is not accurate. We use drone data, Dynamo, and Google Maps to generate accurate topography data for optimizing design and construction plan.
The first response system at stage 1 of the flooding is the SUDS roof. The SUDS roof has a 2 millimeter layer that can store water in up to 24 hours, minimizing the risk of surface drainage. The water from the blue roof will be led to a sprinkler tank underneath the building used for fire safety. The gray water from the showering and washing hands will be utilized for flushing toilets. By having this water loop, we minimize the use of water as seen here on the STV diagrams.
And these 4 types of vegetation can grow without maintenance on our roof. They are all well draining, and they preserve the ecosystem in the park.
We also implemented a moist monitoring system called SmartX by their company Progeo. It consists of a thin layer of an electrically conductive material which is placed under the ceiling. It locates leakages where water enters precise and sends a signal. Since we have a wooden structure or even building, water is a big factor of danger. Leakages will occur sometime, but they are not noticed for a long while and can harm a lot. With this system, the damage can be located and repaired immediately.
As you can see on the chart, the investigated system will help to reduce the impact of damage tremendously without being overly expensive to either install or maintain.
There are 2 key aspects to industrialize the roof. First, to reduce the amount of dirty work during the finishing stage of the roof, and the second, we have a restricted site, thus we cannot handle the storage of the roof materials. We decided to make use of the unique roof component, the SUDS layer, in helping connecting the solar panels with the roof, to install the steel corrugated sheet, which is the base of the solar panels on the SUDS layer, and then connect it with a square hollow steel section in which it will connect the legs of the solar panel, and it will be used to be lifted by the tower crane. We thought of installing the roof panels with the solar cell on them. We made the study and found that it reduced cost and time and workflow on site, since it requires only one crew on the roof. However, there was a big disadvantage that we need a high number of transportation trucks, which is a turning key in our decision as it will cause a lot of problems. Therefore, we chose to have only the roof panels to be manufactured off-site and solar panels to be installed on-site. This will solve the problem of transportation since we need only 5 trucks. This will save us more time and cost, since we don't have to pay the crews for extra days, although we might need some coordination between the solar panel crew and the roofing crew.
And the second stage is landscaping, which is working against the flood after 100 years. And here do you see how the water reach and how the landscape will look before and during a flood. And we're utilizing a green gutter around the flooding part of the building, where there is trees and berry bushes to suck up the water. This vegetation can sustain weeks of flooding at a time. Berries can be eaten by the occupants. The public pathway is inspired by the cobblestones from the park, but we put grass in between, which makes them one of the most well-draining floors on the market. From the entrance, do we have a slope down for all the wheelchair users? And we have stairs and sitting stairs both for the public and for the occupants. The landscape that is inspired by the castle, which is a stone building with wooden shutters, we want to invert that, so our landscape is a stone and our building is the wooden part that is growing from here. The plaza is lifted up to prevent flooding into the building, and the public pathway is what you see in the render here, and also the draining gutter.
Tree location plays an important role of flood protection as well as landscape design. Out of 18 trees, 12 trees will be kept and will be protected during construction. 6 trees, including chestnut, will be effectively placed around the plaza.
As third part of our design system, we are using amphibious or manual flooding walls to prevent entrance of 200-year flooding and keep our building dry and possible to use directly or during the flood. Flood walls can respond automatically with water pressure or manual because time of flood can be predicted. With this system, we are giving robustness to response and increased performance. With allowing our walls to be automatically lifted, we get rapid response system in case of unpredicted flooding. In stage 4, we considered our building as flooded. This is the least likely scenario, but because future is unpredictable and we want to have adapted building to future climate change, we added additional protection. We included in our design various number of materials that are flood resistant and can be dried and maintained with ease. With additional protection, we ensure that response system sacrifice only parts of the building that can be replaced or maintained with low cost. In such scenario, when our building gets flooded, we are giving additional protection to MIP appliances to ensure reliability and reduce damage cost. With design system that can fail modular, we are having redundant flooding protection that ensure predicted and safe failure.
This chart shows the impact of the stages 1 to 4 in our calculated risk cost. The annual risk charge at stage 4 will be down at 155,000 euro to cover all risk. In the upper right corner, the risk is still uncaptured. The landscape will drastically reduce the impact of the flood to the risk. However, the building itself is not protected since water still might enter without being stopped. The mechanical flood protection walls will stop the water from entering the building as we see at stage 3. Anyway, we have to be prepared for a flood, and the impact will be reduced by choosing the right interior materials and protecting our sensitive tech.
And this is how our facade looks like. And we are getting inspired from geometric grid, from the city analysis, but also from the existing Weimar University building where there is this 45-degree slant on the roof. We are utilizing this to get more daylight into the offices. And our facade consists of 4 basic elements: the grid for the architectural impression, but also for prefabrication. We're doing Louver Design for shading. We are having these rain chains in copper that relates to the tower, which is utilized to protect the facade from rain together with the growing ivy plants.
Facade details are designed for aesthetic, performance, and construction. The bioextram structure layer and the insulation layer are arranged alternatively, and the composite use of aluminum frame and wooden grid ensures water sealing performance between the modules. The integration with internal heating panels significantly minimizes the construction process on site. Each module is arranged according to the layout of the room, position of the window, and floor height. As a result of equalizing the size and optimizing the layout, 79% of total 230 panels are standardized. Each module is broken down into kit parts using Kit Connect application, and the model is managed to streamline industrialization. The price of material increases due to the labor cost in the factory, but the benefit of reducing construction labor costs and schedule are huge, with ARIS simulation confirming 36-day schedule reduction and 470,000 euro reduction on-site labor cost.
For the facade, we set up a script in Rhino to see how we could minimize the heat gain to avoid fluctuating temperatures. We inputted vertical louvers on the west facade and horizontal on the south facade. The width of the louvers and the angle were our parameters. 3 options were found to be the best for the south facade, and more good options were found for the west. To easily prefab the facade, we chose only to look at the 3 best options that the 2 facades had in common.
And here do you see options for number 5, number 8, and number 11, where the green color for the daylight is the good one. We chose option number 5 according to architectural impression. But then we looked into which angle we wanted, and for the user, the 25-degree angle is the best because you have a better view towards the outside, and both louvers actually blocks glare from the sun in the sun direction of the room. And here do you see the cover chains. They protect the facade from rain and lead the water down, but instead of leading it down to the ground and increase the flood, there's implemented some boxes for the plant on each floor, so the water that can water the plants, and the plants can grow evenly on the facade. And here do you see how the Buttercup is expressed on the facade. The design relates to how the sun is impacting and therefore creates a different expression and different facade orientations.
From here, we are going to explain specific information for construction. We are in the middle of heritage area and have access from public from north and south. Minimum road width is 3.5 and the maximum track width as per the regulation is 2.5. Our building just fit the site and there's no space on both east and west. There are 2 laydown areas at north and south and 2 gates. The difficulty of material handling on slope ground, a tower crane is installed on the southeast side of the building. A semi-construction area will be provided to mitigate the impact of construction vehicle on the surrounding area. It is usually open and enclosed by a simple fence, but this area will be closed when there is a delivery of large vehicle or concrete. Since the tower cranes use the floor panel size and the crane position is optimized using dynamo to shorten the schedule as well as reducing size of crane. For structural members also, the position of crane is optimized according to the weight and distance to each member using dynamo. We plan prefabricating bathroom and the architectural plan is made according to the side limitation and access for installation. All the finishes as sanitary fixture will be installed off-site and will be delivered as a box during structural work. Because our floor do not have concrete on top, we can install a bathroom box during structural work, which allow us to proceed with the finishing work around the toilet right after the finishing stage, right after the structural phase. With this method, material transportation cost increases, but we can save installation, especially the schedule can save almost 2 months. Schedule verification by ARIS confirmed that the work would be completed in 152 actual working days. This analysis considers the impact of rainy weather on external operations. 36% of crew utilization increased to 48% through optimization, while labor and crane cost is minimized.
This is an example of how artificial intelligence and VR can work together to become part of our decision-making process. We checked the schedule coming from Alice. We found that October 14th is a very intensive day, since we have 3 activities to occur. The activities were erecting roof panel and facades for Zone 3, pouring the slab on grade for zone 1. This is hard since we have a restricted site, as our site cannot handle having 4 equipment at a time. So we checked the schedule again, and we decided to push the pouring of slab on grade 8 days without delaying the total project duration, since this activity is not in the critical path. It's important to mention that the semi-construction area facilitates the truck entrance, as it allows room for turning radius into the truck both south and north gate. This video shows the construction peak flow. First, a truck entering the site from the north gate, and the tower crane lifts the panels to be erected on the roof. Then, at the same time, our site is getting ready to welcome the other truck having the facades from the south gate, and the crane starts to lift the facades to be installed. This is a construction sequence on our site. We start by piling in zone 3, then excavation for zone 1, then zone 3 and zone 2. Foundation work starts from zone 1, and then zone 2, and then zone 3. Then the skeleton work will take place right away. We extensively work on zone 3, so we utilize all the manpower to finish zone 3 skeleton, and then working on the facade for zone. We make sure to pour the slab on grade before doing the finishing work and the MEP works. For the finishes, we keep the sequence, start from zone 3, then zone 2, and finally zone 1. At the same time, we start the facade erection for the remaining zones, and at the end coming the roof insulation and the installation of the solar panel. Finally, we end our construction work with the finishes for zone 1, third floor. Budget value is 8.69, and our target is 8.21 million euros, which is very reasonable when compared to the average cost per area, according to the European construction chart. Pie chart on the right shows the target cluster distribution. We use 100% model-based estimate. We extracted the data using a Rhino script. Our code database comes from German contractor database. We also take some information from the US mentors and RSMEs. We also make sure to apply a location factor. We keep tracking of our cost evolution throughout our journey. Here's the key milestones for the changes in our cost. We started with a pure cost guesstimate in February 16. Then we refined on the winter presentation after having some reliable cost estimate and more developed model. Then afterwards, on the 20th of February, the cost has increased since we increased the excavation by the request of the engineering team. Thus, the substructure cost has also increased. Therefore, we have some major changes in the interiors and the core walls. On the 13th of April, the costs were reduced as the structural framing has changed from the global beams into trusses, as well as facade design, finishing materials, and ceilings were more developed. As such, the costs were accurately calculated. Towards the end, the cost has also increased due to the design of the flooding protection system and the landscape. We ended up with a total cost of 7.7 million euros, which is below our target value.
We have total lifecycle cost of 19.2 million euro. It splits into 1/3 construction, 1/4 risk management, 2/3 split up to replacement, financing, and operation maintenance. Most notable is the well-reduced building supply due to our low dependence on the electricity grid. Our personnel costs are split into cleaning, caretaking, and property management. The previously mentioned cloud service is responsible for 5% of the total cost. Loan life coverage ratio, shown as the bright graph, and debt service coverage ratio are the benchmarks used to describe the ability to repay outstanding debt. Both are necessary to get funding from banks as well as owners, and they are necessary for us to elaborate whether we are within our financial limits at all times. DSCR and LLCR must not fall below the horizontal bars at any time. All our effort to create a sustainable building will be evaluated by the DGNB after the initially introduced criteria. All these requirements are fulfilled to complete satisfaction. Frequent adjustment to these requirements during the design phase not only helped us evaluate on our decisions, but also will ensure that this building will be future ready and enjoyable for generations of students to come.
The STV evolution shows the biggest changes throughout the design phase. The excavation did not improve the STV parameters, but was necessary to create pleasant floor heights for the occupants. Changing the glulam beams to the trusses helped since the amount of material was reduced. To reduce the flood risk and utilize the rainwater in the building system, we implemented a blue roof, even though it had a negative impact on the STV.
With facing the resilience challenge, we managed to achieve next goals for social and climate resilience. With flexibility of our design, we also achieved the possibility to reorganize our building and use it as part of the pandemic response system. We are also helping the city to lower disturbances and help in case of unpredicted events, such as future pandemics, by giving shelter and help to people in need.
With redundant and modular response system, we achieved high flexibility and possibility to quickly shift from resistance to recoverability after flood. With including landscape in our design response, we are adding additional value to it because it co-benefits our building user and local ecosystem. With different sensors, we are giving our building option to adapt to future climate change and increased risk of climate hazards.
This is a summary of how we tackled the TPR challenge. We studied 5 items, all of them require 2 or more discipline integration. We assessed the risk and reward using 11 criteria, spanning over 5 categories. We assign different weights according to their significance. For example, we assign high weights to cost and schedule reduction and give less weights to maintainability, as we can sacrifice for the sake of all other metrics. All the prefabrication was beneficial in increasing the flexibility and operability of our building.
Here's a summary of what's relevant to IT challenge. We use available software to interpret on several items from each discipline. In particular, the facade design was examined in a wide range of areas from visual analysis, shape, performance, cost, detailed dimensions, schedule, and construction method to create an optimum design. Also, MEP and the structure design interpret size of duct, beam, performance, and visual analysis. Flood analysis use multiple data points from drone data and Google for simulation. Structural system coordinated parametric analysis of construction to find the best design and plan.
Our communication, coordination, and collaboration process is best described as this pile of wood. We heavily depend on the lower levels of software and tools that are the cornerstone of our whole decentralized team process. The extra touch is created by the more sophisticated tools at the top of the pile. The big challenge for all of us was to get familiar with the sheer amount of opportunities these tools offer and how to explain our discipline standpoint without sitting together at one table. We used cloud technology for simultaneous group work and held daily virtual meetings on Zoom. We elaborated design changes and clash detections with VR walkthroughs almost on a daily basis. We structured our tasks with Asana to stay within our schedule.
This is an example of how VR impacted our design, not only solving disciplinary and cross-disciplinary issues. VR has helped our team to find ways to utilize every space in our building. We also run simulations and finally get inspired and enjoy our building. This is how our team evolved from strong BIM manager team to a strong BIM team. We set our rules and protocols that were followed by every member in our team, as we believe that being a strong BIM team is a responsibility for each one of us to deliver top quality 3D models.
We created a digital overall pool planning at the beginning and converted to Asana task. This allowed us to proceed efficiently with each individual task. Dependency of each discipline significantly improved in the spring quarter by knowing what others really need. Degree of centrality became well balanced and resulted our great project. Working time record shows working hour increased as the project progress. In particular, there is a significant increase in time spent on meeting, and instead, the rework rate decreased after we started stand-up daily meeting. Ratio of total working hours with discipline shows architects spend the largest amount of time for the project. Asana task record shows 411 tasks were completed in 2,500 hours total. We each believe this project turned out to be an invaluable experience for our career. We thank all of our supporters for the project. And with this, we conclude our presentation. And thank you all again being with us.
Thank you, River, for such an amazing effort and exciting project. We look forward to the mentors' questions and feedback and wish you all the best in your future endeavors.